Good afternoon, everyone. My name is Yunxin Wu. It's my pleasure to present our work in IROS conference in Japan. So my talk is about modeling and position control of HASEL actuator using the port-Hamiltonian approach. The hydraulically amplified self-healing electrostatic actuator, the HASEL actuator for short, has been developed in several years ago. So this actuator has shown in different applications due to its advantages. This actuator can generate a large deformation, and its response is very fast. And due to the dielectric liquid inside the actuator, this actuator is self-healing, and the consumption of the power is quite low. And also this actuator is soft contact. So the working principle of the HASEL actuator is the following. So this actuator is built by a flexible polymer pouch with the dielectric liquid inside, and this pouch is half covered by electrode. When we apply the voltage on this two electrode, it can generate the Maxwell force, which zip the shell and push the liquid, which generates the deformation of the actuator. So secondly, when we turn off the voltage, the actuator will go back to the initial position thanks to the gravity force. The quasi-static model and the simple control law has been investigated in the literature. However, in our study, we want to propose some control-oriented dynamic model and apply some advanced control strategy on this actuator. The difficulties are this actuator has high nonlinearities due to its geometry nature and the multi-physics nature. To handle those challenges, we propose to use the energy-based approach, namely the port-Hamiltonian framework, to deal with these two challenges. So the geometry, so before the modeling, we do two assumptions. Firstly, the geometry of the actuator, we simplified from applique 1 to diamond 1. And secondly, we approximate the liquid hydraulic mechanism to two mass spring damper systems. And then the total energy of the system can be written down in this form with the potential energy, kinetical energy, the electrical energy, and the gravity energy. And the energy variables are chosen as the displacement, momentum, and the charge. Then we define other co-energy variable, which is the derivative of the energy with respect to the energy variables, state variables. Then we can write down the port-Hamiltonian model of this system. With the skew symmetry part is the energy exchange between the different components of the actuator, and the diagonal part is the energy dissipation of the actuator. And the V is the input of this actuator. And then after the modeling, we use the interconnection damping assignment passivity-based control, IDA-PBC for short, to design a control law. The idea of this control law is to design a control such that we can map the open loop system to a closed loop system with the desired energy of the closed loop in the closed loop. The desired energy contains the desired position and the desired dynamic behavior. And to improve the robustness of this controller, we add a structure-preserving integral action to make sure the robustness of the controller. So this is the overall closed loop block diagram. To validate the proposed model and test the different control laws, we use this experimental setup. So first, this baseboard can generate the control law and get the measurement data. And the high voltage amplifier can amplify the voltage and get the current measurement. And we use the laser sensor to measure displacement of the actuator. And the load container can allow us to change the mass load easily. First, we use the nonlinear identification toolbox to do the identification. We apply different voltage and the different mass load to get the measurement data, and then we use the optimization procedure to get the parameter of the spring and damper. And then we use the IDA-PBC control law, the proposed ones, to control the actuator position, which follows the different shape of the position references. And then we test the robustness of our controller via the external disturbance rejection. So here, when we apply the integral action in the controller, we can reject the external disturbance quite easily. The position always follows the desired ones. So to conclude our study in this work, so we propose a dynamic model with the port-Hamiltonian approach, and also we design a position control using the IDA-PBC control law. So in the future, we would like to generalize our proposed model and control law to a complex design of the soft robot based on the HASEL actuator. So thank you for your attention.